Okay, time for another lecture. Been watching a lot of Tiger King lately. Feel as though I should start these lectures with, what is it, all you cats and kittens or something like that. Oh, I gotta figure that out. Cool cats and kittens, right? Is that what she says? Baskin. Anyways, so let's do this. We're getting there. We only have a few more lectures left, and we will be done with steel design. Okay, and this class in general. I've kind of not played around, but I've tried to come up with a way to break down. We're only going to do one lab lecture, right? So what I did is I'm going to get you that one back. I handed the lab lectures to the undergrads before this whole thing went down. They edited those lab lectures. I'm going to give them back to you, and I want you to make those corrections, right? At the very least, we're going to do that. The rest of the points that were associated with those lab reports, I took and spread out amongst all the other categories of the class, and then I also added in some percentage for participation. If you came to labs and did what you're supposed to do, I was going to give you a boost for the lab participation. So take a look at that. Okay. Take a look at how I'm going to break the grades down and see if you have any major issues with it and stuff like that. So I want you to take a look at that. So, God, what was I going to tell you about? Like, you'd think that sitting in my little home office by myself, I wouldn't get distracted, but I am getting distracted. Okay. I told you about lab reports. We got that worked out. We're getting down to the end here. Okay. Well, let's just dive in here. So, we get a lab. You're gonna have a lab final next Friday, and we have and then we have the final of the class the week after. And I'll cover some of those details a little bit later. I'll have a formal little outline of what we have left for the rest of this class. But anyways, we're getting really close to being at the end. All right. So we're in the middle of the flexural design. Okay. And in flexural design, we talk about all these limit states, the design of the moment, it could fail due to local buckling. It could fail due to lateral torsional buckling, or it can form a plastic hinge. If we're doing a laterally supported beam, we don't have to worry about lateral torsional buckling. Okay, so that becomes not a limit state for flexure. And then also, most wide flange sections are made with compact flanges, which means that the flanges will not buckle prior to the plastic moment forming. And so when you're designing a flexural member, a standard wide flange beam, all we have to take into consideration is PMP. We have to make our PMN is going to be the same as the plastic moment capacity, which is going to be phi times Fy times Z. You just need to make sure that this value is bigger than Mu. Okay, and we talked about using these Z tables, right? For doing the design, you could just finished a homework where you got to use those Z tables. The other mechanism that could control is shear. And shear, we're just going to look that up in the Z tables because they have that capacity in the Z tables. But something when they fail from shear, it could be yielding of the web, or it could be buckling of the web. But just like local flange buckling, it's typically not going to be an issue because they make the web stocky enough so that local web buckling does not become an issue. Okay. And when we go about design, we just look up that capacity, and then we check to make sure that our deflections are going to be adequate. And what we did is we talked about looking up those tables in the table 3-23 in the back of the beam tab. It has all sorts of different loading conditions, and you could look up what these delta LL and delta TL are for the different loading conditions that you're dealing with. Okay. And then it's just a matching game, and then you use the equation to predict what those deflections actually are. Okay. Then we did an example. You just finished a homework associated with this. Okay. So then the next thing we're going to talk about is not laterally supported beams. Okay, where you have not supported the beams laterally. And when you have a beam like that, then lateral torsional buckling can become an issue. So we're going to add in a different limit state up here, where it can either be formation of plastic hinge, or it could be lateral torsional buckling. Okay, and so we'll go down here. These are the tables that we use for that example. And here there are the sections of the code right there. Okay, so this is what we're going to get down to here. So this is in the latest packet of notes that I have posted. Okay, and hopefully I will have remembered to post it. So I haven't posted it yet, but I will right after this video. But by the time you watch this video, it should be up. If it's not, email me and say, where are those at, you bastard? We need them. Okay, so this next section is the design of laterally unsupported beams. Just like I said, this is kind of the next topic. What are we going to do when it isn't continuously supported across the top flange, right? Not necessarily the top flange. It could be the bottom flange if it's under negative moment. Whatever the compression flange is what you have to support, because something in compression buckles, something in tension does not, right? And so, you know, oftentimes it could be where you only have it supported at the end, at the top on the ends. You'd support them. You wouldn't just stack this here without any lateral support. Typically, you would at least include them on the ends where the regular supports are. You would have some sort of lateral support there. But then you could also have intermittent lateral supports as well. Okay, you could have a lateral support here, here, and here. And that's what I'm trying to show here. And so you have multiple unsupported lengths in this thing. Okay, and so what's going to control if you're going to have lateral torsional buckling is going to be this distance. What is the distance between the lateral supports? If you have really tight lateral supports, okay, if I have lateral supports, you know, continuous along the entire length, okay, then lateral torsional buckling is not going to be an issue. But if I only support the ends of it and this span is really, really long, then I could have some issues with lateral torsional buckling, okay? But then if I support it midway, you might have less of an issue with lateral torsional buckling, okay? And so this is another capacity curve that comes out of this, okay? And so this is the moment capacity versus slenderness. And so that is just, right, this should be a shape that you're getting used to seeing with steel design, where you have a plastic moment capacity, but after you reach a certain slenderness, okay, or a certain unsupported length in this case. So what's plotted on here, by the way, is Phi-Mn, the moment capacity, versus LB, which is our unsupported length. So it's how big is this spacing between your lateral supports getting. Okay, as LB gets bigger, the beam is more susceptible to lateral torsional buckling, and so our capacity goes down. When something laterally torsional buckles, its capacity goes down. So there it is right there. That's Phi-MP, and then it loses its capacity shortly afterwards. And so just like, I guess we can write these things down. So this would be, call this capacity is Phi-MP. I'm going to put it up top here, actually. Right? That's what that capacity is. You've supported it tight enough, right? This is small enough right here, this distance. You've supported it tight enough that a plastic hinge would form before you get lateral torsional buckling. That's what this would tell you. So it peaks out at the plastic moment capacity, okay? And then, so this line, I'll just draw one solid line. Let me get purple here. Okay. Oh, I think that with the help of a straight line tool, I could draw a straight line. There we go. So where it transitions, so there's a couple transitions here. We'll put one there and one here. Okay, the where it transitions between the plastic moment controlling and lateral torsional buckling controlling is when you hit an unsupported length that's LP. We'll talk about where these come from, but there's a unsupported length of LP. When LB is bigger, when LB is bigger than LP, that means you're over in this range right here, and you're going to have lateral torsional buckling be an issue. There's another value in here called LR. Okay, and what these things distinguish is this. In here, if you fall in this region right here, where your LB, your unsupported length, is bigger than LP, but then less than LR, then that means you're in a region that inelastic lateral torsional buckling controls. Inelastic LTB controls, okay? If your LB, if this LB, your unsupported length, this LB right here, unsupported length, is bigger than LR, then it means you're over in this region right here. And in that region right here, as you might have guessed, this is elastic lateral torsional buckling. Okay, and so you have these different behaviors that happen. What would happen here, so if our LB is really small, it's less than LP, that means you're over here. That means that if I bent this thing, I apply a big axial load on this thing, if I applied not axial load, but a transverse load on here, what would happen is I'd form a plastic hinge wherever the maximum moment is, and that would peak out, and that would be my ultimate capacity. But if LB is bigger than if LB is bigger than LP, but then less than LR, then it means I would have inelastic lateral torsional buckling with control. So this thing with the top flange would buckle out, but it wouldn't buckle out in an elastic fashion. It would buckle out in a plastic fashion, right? Which means that there'd be permanent deformation. There would be yielding. So when the thing buckled, it would be a little combination between elastic lateral torsional buckling and it'd be a combination between the formation of a plastic hinge and lateral torsional buckling. So it would kind of fold on its side and yield. And so when you remove the load, you would have permanent deformation, okay? And that would be if your LB is greater than LP and less than LR. But then if this LB gets big enough, if our unsupported length gets big enough, then LB is bigger than LR, and you get elastic lateral torsional buckling, which means if you applied a big load on this thing, eventually this top would kind of pop out, but everything would remain elastic, okay? And then when you remove the load, it would go boop, and it would pop right back into being straight, okay? And so that would be considered elastic lateral torsional buckling. When you get elastic lateral torsional buckling, it's very weak, right? It's way down here. Your capacity is really low. But you could imagine the mechanics, obviously, for the plastic moment, for calculating the plastic moment, is different than calculating the moment for inelastic lateral torsional buckling. This has got yielding going on in part of the beam and not in other parts. And then the mechanics would be completely different for elastic lateral torsional buckling because everything would be remaining elastic. Okay, and so the code accounts for these three different types of behavior, right? And so in a second here, we're going to look to see what the code says, right? And we're going to see these equations that say, yep, if LB is less than LP, it's VMP. If LB is greater than LP and less than LR, then they're going to give us an equation for this region right here, which is going to define this curve. And then it's going to say, well, if LB is greater than LR, this is what your equation is, okay? And so stay tuned for that. Okay, well, actually, let's talk about it right now. So, well, I'll show those to you in a second, but just going to put some of this stuff down. So these equations, our capacities, are in chapter F. Okay, of the code of the AISC. Something else I wanted to say. Oh, they're huge equations. Biggest equations you've ever seen. Yeah, they're pretty big and they get pretty complicated. And the other thing that we can find, LP and LR are also huge equations, but are tabulated in Z tables. Right? If for some reason you need LP and LR, remember LP and LR are the three R's in a row. LP and LR are these guys right here. LP and LR, right? They're the borders between these different types of behavior. You can look these things up for each type of member that you have. Okay, it's just kind of a helpful thing that can show up in those Z tables. We won't end up using those there too much. There's also another tool that we're going to use for design in a few minutes. Okay, but just as something to mention there. Oh, but then you also have to design each unsupported length. Okay. You have to design a beam for each unsupported length, which we're going to do in examples. So you can kind of see all that at play. But if you have like this, where I've got this unsupported length, and a maximum moment and stuff like that, I would design for this unsupported length and come up with what size beam I would need for this unsupported length. Then I would design for this unsupported length, see what beam I would need. And then the overall beam would be the biggest beam, the worst case scenario here, okay? Would be how you would design this. But we're going to see that play out in examples in a minute. So let's look at these equations in chapter F. I think I provided them up here. All right, so this is chapter F. F2 is for doubly symmetric compact I-beams. That's what we're going to be dealing with. Okay, and so it comes in and says, all right, what are our failure mechanisms, right? That's what this is. That's what this is. So this is the specifications tab, chapter F in the specifications tab. I put a tab on this sucker, right? So when you're taking the exam, you know right where to look for it. Okay. And so it says, yep, one of the failure mechanisms or one of the limit states is going to be yielding. And in yielding, we calculate MN is just going to be MP, and MP is calculated FY times Z. And this is what you kind of did in your last homework. This is the only failure mechanism that controls. Okay. The other thing while we're here, I should also mention too that when we say that having compact webs and compact flanges. Remember I said most wide flange sections have compact flanges and most wide flange sections have compact webs. Well, here are all the ones that do not meet those requirements. Okay, and so those specifically it calls out, right? W21 by 48, 14 by 99, 14 by 90, 14 or 12 by 65, right? Just a handful of them that don't have compact flanges, right? And they've done that on purpose. They don't want local flange buckling to be an issue, so they beef those suckers up so that it doesn't end up being an issue. Same thing happens for compact webs as well. Okay, so anyways, there's the yielding mechanism. I just wanted to point that out. I usually point that out earlier. So this is the yielding. This is how you calculate the capacity for yielding. But then it comes down and says, all right, let's now look at lateral torsional buckling might be an issue. It says when LB is less than LP, the limit state of lateral torsional buckling does not apply. So it just says, yep, when LB is less than LP, then it's plastic moment's the only thing we have to deal with, right? So that's just to the left of that little curve that I drew before, right? That's all it's saying is it's just that region right there. Then we go on and says, well, if LB is greater than LP and less than LR, use this equation for calculating your capacity, right? And so this is where we have, this is inelastic. So this equation calculates the capacity of inelastic lateral torsional buckling, okay? And these mechanics are governed by that, okay? And that one doesn't look too bad, right? And it's got the CB. We'll talk about that a little bit later. But then, it's got an LB and an LP floating around or an LR floating around. So this one doesn't look too bad. Unfortunately, when we dive in here a little bit closer, you'll see that LR is a pain in the ass to calculate. So is LP. But then you can also look that up, right? And so, but anyways, here's what the moment capacity is when you're between LP and LR. Then you come down and say, well, what if LB is greater than LR? Here's the equation for calculating that. That one looks pretty easy, right? MN is just FCR times SX. But unfortunately, if you come down, right, there's FCR, right? A lot of stuff going on in FCR. Again, there's that CB value, which we'll talk about a little bit later. That's out front. But then that's how you calculate FCR. You multiply that by SX, and it gives you that's going to be way out here on the right when LB is greater than LR, right? And then you could see, oh, this is what LR is, right? Right? That's a huge equation for calculating what that unsupported length is, the border between elastic lateral torsional buckling and elastic lateral torsional buckling. Right? This is going to be paid about. Good news, though, right? These are just section properties, properties of the section. So these things can be pre-calculated. Both LP and LR, they're in the Z tables, okay? But then also, we're not going to use these guys too much because we can, one, you can look them up, and then two, there's a design aid to help us through these designs, okay? So those are what those equations look like. I just wanted to show you those. Oh, no, I'm getting ahead of myself. Okay. And hopefully you kind of see what it is, how we design for lateral torsional buckling, and hopefully too you see why we got to put that off while we're learning how to do the shear design and the moment design and checking deflections. Okay, but now we're going to do these laterally unsupported beams. Okay. Okay, so then what are things that control this behavior, right? What's going to control, am I going to get a plastic moment capacity? Am I going to get inelastic lateral torsional buckling? Am I going to get elastic lateral torsional buckling? What about the property is going to govern that behavior? Also, what's going to govern the overall capacity, right? Here, Z is controlling the capacity. But what's controlling the capacities out here when I go to calculate those things, okay? So one of the things that obviously is going to control that capacity under lateral torsional buckling is going to be the unsupported length, right? unsupported LB, right? Obviously that's going to control where am I at on this curve, right? That obviously, right, there it is. There's a plot of phi mn versus LB. You can see that LB obviously controls the capacity. So unsupported length, that one kind of goes without saying, but we're going to say it anyway. That's one of the things that control it, okay? The other thing that could control it would be properties of the cross-section. Right, what do I mean by that? Well, and material. Right, both of those things. Properties of the cross-section and the material, right? Obviously, you know, if A is bigger, it's going to be less likely to have lateral torsional buckling. If E is bigger, it's going to have less likely to be lateral torsional buckling. If your I is bigger, you have less likely to be lateral torsional buckling. If J, right, which is, I forget what J is. We'll look at that in a second. But that's a section property. Similar to I, but there's a J. I forget what it's called offhand. CW is another thing, which is a warping factor. Okay, is one of the things there. And then obviously the yield stress of the material. All of those things are going to control where we're at on this curve, right? You know, if, like I said, if E is bigger, you're less likely to get buckling. If I is bigger, you're less likely to have lateral torsional buckling. J, unfortunately, I forget what J is. CW is the warping factor. J, that's driving me crazy. What is J? J is the torsional constant. Oh, something over JG. Calculating the deflection of a... Oh yeah, calculating deflection of something in shear, use the J value. Right, or torque. It's torque on a circular member, use J. PL over JG or something like that. TL over JG. I don't know. That's back to mechanics of materials. Anyways, those things, those properties of your section and the properties of your material are going to control what's happening there. The other thing that's less, and these both are very obvious, right? Unsupported length and then the section properties. The thing that's less obvious would be the end support conditions or the support conditions. Okay. How much of beam is exposed to high moments? Okay, that's a simple way of putting it. That's where it really affects things. So that's what these next little graphs are to illustrate. Okay, so if I have a beam that's just simply supported like this, okay? I have a uniformly distributed load, and I have a pin connection and a roller connection on this. So my moment diagram is going to look like this. Something similar to that. That's a better one, okay? It's going to be, the moment's going to look like that. Okay? And then versus over here, this is the same type of thing, same load. Assume this is the exact same load. Right, and in this case, I have a fixed support at the end, as opposed to just a pin and a pin. So pin and a pin, we have 0 moments. If I have a fixed end and a fixed end, this thing's going to start out with negative moment and go to positive moment. And so it would basically just be, well, I think I could just do this. I think I can go. It's the same curve. It's just it starts out as a negative moment instead, okay? I guess it didn't work out as well as I thought because these guys are... There you go. Okay? It's the same curve, it's just shifted down because of the negative moments that are up front. So we have this case right here and this case right here, okay? So the exact same loads, right? Exact same loads applied, but it's this guy versus this guy. Now, which one do you think is more susceptible to lateral torsional buckling? Right? You know what's really funny is that I was sitting there waiting for one of you guys to answer. It's like I don't even know you're not here. Okay, obviously you're not here, so you can't answer this question. Okay, but the answer is this guy is more susceptible. more susceptible to LTB. Okay, and the reason it's more susceptible to LTB is because if you look at this one, this guy right here, you know, it starts out at 0 moments at the end, but almost the entire length of this beam, actually the entire length of the beam, that top flange is going to be in compression. This is a positive moment, right? The positive moment means you get compression at the top and tension at the bottom. In this case right here, almost the entire length of the top flange is undergoing compression, okay? Whereas over here, the only part of the beam that has compression is that portion right here, okay? Right? Hopefully everybody sees that. This one, the entire length is in compression. This one, only from here to here is in compression, right? Out here is a negative moment, right? It comes out, it bends down like this, right? And so you have negative moments near the ends, and you have positive moment in the middle. And so the only place you're going to get compression, right, you could maybe have lateral torsional buckling issues over here because in this region you have the bottom in compression, but just for the example here, only between here and here has compression, right? And so then when you're designing, so say, I guess I spoke wrong earlier. Think of these things having not having the same loads, but having the same max moments is what you want to do. So say they both had the exact same max moments. Actually, that's probably be clear that way. It doesn't really change the argument or the discussion at all, but it's not the load, because you're right. You might be going, well, the one with the less moment is going to be the less likely to have lateral torsional buckling, which you would be right. Imagine, though, that they both have the same positive moment. Okay, so they both hit that same peak. I think I drew it right there. Right, so they both hit the same peak right there. And so they both hit the same peak, but even with the both being the same peak, this guy on the right is going to be less susceptible because only the middle part is in compression, whereas this thing, the whole thing is in compression. Okay, and so the way we account for this is with the CB value. Okay, I'm gonna clean that up a little bit. I'm gonna type that sucker. It is more susceptible to LTB because more of the compression flange, or more of the flange is in compression. Yeah, more of the flange is in compression. Account for this with CB value. Okay, and I showed you that before, right? I pointed that out in those equations. I said I circled CB a couple of times. That CB that's floating around in those equations are to account for this different behavior. Okay, and so we're going to talk next about how do I calculate CB, right? How do I calculate CB so that, you know, here I get a bigger CB and over here I get a smaller CB. So CB was multiplied by the capacity, and so the CB will increase or decrease your capacity. CB greater than 1, it would increase your capacity. CB less than 1, it would decrease your capacity. Now, so how do we calculate CB? So that's the next step. Hopefully everybody understands the difference here and why those need to be in the capacity equations, right? Because those loading conditions, this is less severe than this over here. Right, because only the middle part of the beam is in compression, whereas this whole length is in compression. Okay, so how do we calculate it? Okay, so first off, this is the loading condition. Right here is the worst case scenario that you can get when you have a moment here and a moment here. Okay, your moment diagram would look like this. Okay, and this is the worst case scenario you can get. Here, the entire top flange would be in the maximum compression. right? Over the entire length, right? The biggest moment here would give you the worst case. The bigger the moment is, will give you the most compression at the top. Well, in here, where I have a constant moment on either end, I have the worst case moment across the entire length, which means my top flange is in compression, the maximum compression over the entire length. This loading condition right here is CB equal to 1.0. Right? And so that is the worst case scenario. So it's always conservative. Always conservative to assume CB equal to 1.0. Right? Because that is the worst case scenario there is. And so those equations that I showed you before, if you assume CB is equal to 1.0, this is how it's calibrated. Equations are calibrated to this value. I probably should put that. Equations calibrated. Okay, the equations are calibrated to CB equal to 1.0. Okay, and to this loading condition. Okay, to that loading condition right there. So how do you calculate it otherwise, right? If we want to sharpen our pencils and we don't want to just CB equal to 1.0 because that could be overly conservative, how do we calculate that capacity? Okay. And so that's what this section of the code is. Okay, so this comes out of the beginning of chapter F. This is F1. You can see here. I just write that down. Chapter F1 is where you find that. Okay, if you open up that section in your text section, it's included above in the text snippets or the code snippets that I gave you. Well, you calculate CB as being equal to this value right here, 12.5 times M max, divided by 2.5 M max, divided by, or plus 3 MA, plus 4 MB, plus 3 MC. And what is M max? Well, M max is the maximum moment in the unbraced segment that we're dealing with. Okay, and we're going to do an example where we calculate CB in a few minutes here. MA is the quarter point, MB is the half point, MC is the 3/4 point across the span. Okay, so in this particular case, what I've shown here, this is the point load. So if I have a span like this and I have a point load applied to the middle, this is what the moment diagram looks like. Okay, that's what the moment diagram looks like. And right, CB will be less than 1. Right, CB equal to 1 is this, and so CB is going to be less than 1 because it's not the maximum across the entire length. It starts out at 0 and works its way up. Okay, but to illustrate what these values are, you would do it for each unsupported length. But if we assumed that this thing was only supported here and only supported here, then in this particular example, right, this right here would be M max. Right, and it would be also equal to MB. Right, MB is the absolute value of the moment at center line of the unbraced length. Okay, and so that's M max and MB, and then MA would be here. Right, and then MC would be here. Right, where this is, right, just to make that clear, that is 1/4 L. This would be obviously at the halfway. Right, and then this one would be 3/4. Okay, and that's it. So that's how you do it. You literally you would calculate. You're going to have to do this. You're going to have to set up your moment equation as a function of x so that I can calculate these different moments. And so when you use this equation up here, well, it'd be 12.5 times this number up here. Okay, and then it would be divided by 2.5 times this number. And I should point out M max and M max and MC don't always align. They just happen to do that here. Okay. And then MA I'd look up, I'd use my moment equation to calculate what MA is, and then MB is this one right here, and then MC is this one right here, and you can calculate those. And again, it wouldn't necessarily be, they don't always, Mmax and MB don't always line up, okay? If for some reason, for example, if I supported it here, here, and here, well then now for the unsupported length, okay, I'd be looking at this section of the moment diagram, and MA would be here, MB would be here, MC would be here, and Mmax would be here. And we're going to do an example like this in probably the next lecture is when we'll get to that, okay? But then you would do that there, and then you would do it for this span, this direction as well, right? In this case, it'd be symmetric. It wouldn't be so bad, but that could happen. Okay, the other thing, so that's how you calculate CB. That's why we account for it, is because we're looking for the severity of compression in your compression flange, how much of the top flange or the bottom flange of its negative moment is in compression, right? And that'll determine the severity of lateral torsional buckling. The other thing is, and that CB accounts for that, right? And we'll calculate the CBs to account for that. I think I keep misspeaking. CB is equal to 1 is the worst case scenario, which it is calibrated for, okay? But the CBs will not be less than 1. They're all going to be more than 1, because for this case right here, right, that's less severe, and so you should get rewarded because this case right here is less severe. And so a reward would mean your CB would be more than 1, right? It shows up in that capacity equation. It'll be CB times your capacity. So you should get an elevated capacity when you have a less severe case. So these cases, both this case and this case, my CB would be greater than 1. Okay, in this case, my CB here would be greater than the CB here. This you get rewarded more because it's less likely to have lateral torsional buckling than this case. So I think a couple of times earlier I misspoke and I kept saying that your CB would be less than 1 for these cases. There'll be more than 1 in those cases. Okay, so hopefully that adds confusion to the already confusing lecture we're talking about. See, this is why it's great to have you in class. You guys would have caught that. You would have said, hey, listen here, Mike, that doesn't make sense. Okay? CB will be greater than 1 the less severe things are. Okay, so here are some examples of CBs. Okay, if you have, this is the case that we just talked about up above there. If you have a case where you have just a point load in the middle, okay, and we have no lateral support, right, your CB would be equal to 1.32. Okay, if I have the same case and I had a lateral support right in the middle, then it ends up being CB is equal to 1.67 for each span, right? And how do they get those? They just carried this out. Okay, same thing with 2-point loads. They talk about what the CBs are, whether or not you have supports at the location of the point loads coming in. Sometimes those point loads coming in actually add some lateral restraint to the beam, right? And then they talk about how you go about calculating those. There's 3-point loads and then distributed load. And then are you supporting the distributed load nowhere in between? Are you supporting it in the middle? Are you supporting it at third points? Are you supporting it at the quarter points? Okay, and so they talk about all the different CBs there. So sometimes it'll fall under one of these categories. Okay, and so they pre-calculate some CBs for it. And this is right at the beginning of table 3-1, which my guess is at the beginning of the beam tab. Okay, and so before we get to so we're almost there. So we say, well, how the hell, right? This is we have the equations for calculating capacities. We know that they're going to be functions of the CB value, the severity of the compression in one of the flanges. We know that it's going to fall into one of these categories. We know that those things are going to be a function of LB, A, E, I, J, C, W, and F, Y. But how the hell do you go about designing these things, right? You're not going to like solve for an E that you need, or solve for an A that you need, or solve for an I that you need and then look it up in a table. It's not that clean. There's all sorts of stuff that's floating around, a lot of things that are controlling it, okay? And so that's where these design aids come in handy, okay? So let's just talk about those design aids real quick, and then I'll show them to you and we'll finish this up. So the design aids that you have at your disposal throughout this whole thing, just for all of beams in general. You're going to have Z tables, Okay, we've talked about those before. We've used those before. Okay, these are really helpful when plastic moment controls. They also include LP and LR and I. Right, so LP and LR are going to tell us lateral torsional buckling going to be an issue or not. I is going to be there to help us with deflections. Okay, they also they also include L and phi VN. Right, that's nice that they have those tabulated in there as well. Okay, the other thing, it's one of the things. These are used. Use these for laterally supported beams. These are really helpful for laterally supported beams because lateral torsional buckling isn't going to be an issue at all. Okay, so that's one of the design aids. Okay, the other thing that we can use is the I tables. We've used those before. I tables. Okay, used when deflections control. Right? They've arranged these things in order of increasing or decreasing I's. So just because I's don't increase at the same rate as the Z's increase. And so that's why they have this other table where that they've ordered all the specimens in terms of I's. Right? It's beautiful. Okay. There's another thing called a max uniform load table. I never liked those ones, so I don't really ever use those. But that's another one. We don't use these. Okay. There's another one that's floating around. So if you have if you know what your distributed load is and you know what your span is, they have some tables to help with that. And like I said, those are less useful because they're like maximum uniform load tables. It's a weird format. I've tried using them before and teaching from them, but I just don't think it's as easy as just using the Z table or the I tables. Okay. And the last thing that we can use, these capacity curves. Okay, and these are going to be table 3-10. It's funny they call it like a table. It's a big plot, and then it takes up many pages. Just like the Z table is like table 3-2, but it takes up many pages. But table 3-10, this is in the beam tab. Right? This would be one of those things that you should put a tab on. You should put a tab on the Z tables, the I tables, and these capacity curves, right? So you know where to look when you're trying to solve these problems, okay? So let's talk about these capacity curves, okay? So if you can imagine, right, for each one, so basically what it's going to amount to, let's talk about these capacity curves. Well, what they are, okay, is for every section out there, there is these capacity curves that we keep talking about. This is phi MP right here. And then as LB gets bigger, your capacity drops off. So you could imagine for a certain beam, like a W24/76, that you could plot what that curve looks like. I know what phi MP is. I know what LP is. I know what LR is. I know what those equations are. I know what I, A, E, J, right, FY. So I can plot for every single beam. Right, there's a W24/76. Here's the W26/36 or by 57 or something like that. I could plot that guy, and then I could give another one right here. This is a different beam out there, and I plot all of those curves on there. Okay, and then you could imagine many pages of these curves that are just stacked on top of each other. Okay, and the way that you use these things, okay, is and we saw this before when we briefly talked about using them in concrete design, is what you do is you plot MU and LB. Okay, so that's this is your demand. Okay, what our moment demand is, our factored moment demand, and our unsupported length is the demand. And so then you plot those on those graphs, right? Or I said on curves. I'd probably say that. That's our demand. And then you read up and to the right, right? Read up and to the right. Anything in that direction will work for design. Okay? first solid line is the most economical. Right? This is back to AISC is no dummy, right? They know, right? They know that you want the most economical beam. And so if you read up to the right, and you're going to see where it's going to it's going to be either dashed or it's going to be solid. And the first solid one you come to is going to be the lightest weight beam that works, okay? The one problem with this is these curves assume CB equal to 1, CB equal to 1.0. These are going to be conservative, okay? Unless you have the worst case, but typically you don't have the worst case loading condition with just a moment on either end, okay? And so that's something to consider is the CB thing. We're going to come back to the CB equal to 1 in a minute. Let's look at what these curves actually look like in AISC, okay? Well, so actually before I get to that, I want to talk about this. The read up and to the right. So what you do is you plot MU and LB. Let me do that on this curve right here. All right, so if I come in, make this red, and say, yep, I'm going to look right here and say my moment demand and my LB ends up right here, okay? And so if you think about it, if my moment demand is there, obviously this one right here, this green one right here doesn't work, right? Because in this case, my MU is bigger than my PMN, right? This is a plot of PMN, so my MU is greater than my PMN, okay? But if I read up and to the right, right, either one of these things would work, right? Or another way to look at it, if my plot is inside this curve, my demand is less than my capacity. If I'm outside of the curve, then my capacity is greater than the demand. Other way around, then my demand is greater than my capacity. If it's inside, my demand is less than my capacity. If I'm outside, my demand is greater than my capacity, and it doesn't work. Okay, and so let's take a look at what that plot looks like. Okay, so these are what those plots look like, right? This table's 3-10. Unfortunately, you can't really see that these are all those curves. Okay, they are. Trust me, they are. It goes on for pages and pages of these things. And what it is they've really zoomed in. If you can imagine, if you took all these things and plotted, and I 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 plotted, right? There's so many different beam sizes. It would be a huge document to try to fit all of them on one page. Doesn't make sense. So they've broken it down and they have all these individual pages and they give you snippets, right? In this one right here, my unsupported length is between 6 feet and 30 feet. So it's over to the right a little bit. It's not starting out at 0. It's shifted over to the right 6 feet. And then the snippet of, or the capacities it's looking is between 1,200 kip feet and 1350 kip feet. So it's looking at the snippet in the horizontal direction and a snippet in the vertical direction. Okay, in the moment capacity and the LB. And you go on to see this next page right here. Now it's going between 1,500 kips and 1,800 kip. Sorry, 1,500 kip feet and 1,800 kip feet. Right. So this is just another snippet of the overall big curve. And in this case, the LB is going between 6 and 30 feet again. Right. And so it looks like this curve right here is stacked on. It would be up here someplace. So it would be up here, right? Is where that one would be if it was all one document, right? And then same thing here. Looks like this one is going between 600 kip feet and 750 kip feet, and again between 60 and 22 is your LBs that you're dealing with. Okay, but it's actually interesting to see here. We're going to see this in an example next time, but you can see that they're there, right? Look, there's the FMP coming across like that, and then this is where LP is for whatever size beam this is. This is a W14 by 99, and so it looks like the LP on W14 by 99 must be 13 feet, okay? And then it switches between FMP, and then this is inelastic lateral torsional buckling. It's going to go down, and then somewhere over here it's going to curve out with the LB is going to be greater than LR. And then you can see here, oh, there's FMP for W24 by 68. It looks like its LB would probably be, or its LP would be about 7 or 6.5 feet or so. and then capacity decreases down like this. Another thing you can see, so like if I was designing a beam and it showed up right here, I read up and to the right, and really a 21 by 73 would work. The 21 by 73 would work. 18 by 76 would work. But if I keep reading up and to the right, I hit this guy, which is W24 by 68, right? And so the W24 by 68 would be more efficient, or would be lighter than a 12 by 106 or an 18 by 76. That's why the 18 by 76 is dashed, okay? And W12 by 106, it switches over to dashed over here, you can see, okay? And then this guy is a solid coming down like that. And so you read up and to the right and you hit the first solid. So I would say I would design this thing as a W24 by 68. It's going to be more efficient than 12 by 106 or 18 by 76. Okay. And like I said, we'll do an example with this as well, but I just wanted to show you these curves, right? And so again, these curves are only for CB equal to 1.0, right? Does that mean you cannot use them when our CB is not equal to 1.0? Okay. Technically, yes, right? And so CB equal to 1.0 is the most conservative. It's always conservative to assume that, right? And because CB is going to be bigger than 1 when it's less severe of a case. But we don't want to over design everything using these curves. So is there something that we can do? And the answer is yes, okay? And what we do is we adjust. So let's talk about adjusting for CB. This one takes a little while to get used to, or to wrap your head around what we do here. But we're going to adjust for CB, that not equal to 1.0, right? Because those curves are only good for that. So what we do is, okay, I'm going to write this thing out. We need to write down some equation. Okay. So what we do is this, right? So mu has got to be less than or equal to phi mn, right? Right. If, no, go down this. That's what it is. If LTB controls, right? If LTB controls, then mu is going to be, right? And for the best design, it's going to be mu is equal to phi mn. Right? And if you looked up the equation for the phi mn, it would be phi times CB times a bunch of stuff. Right? And I pointed out those equations to you before. And so in here is stuff. Right? So that's where your J and your A and your I and stuff like that is going to be in that part of the equation. But if you look to see inelastic lateral torsional buckling and elastic lateral torsional buckling, there's a CB out front of the equations that are used. Okay, so let me actually, might as well just go up and show you, right? This, right? So this is the capacity. This is right here for lateral torsional buckling. So this is inelastic lateral torsional buckling. There's a big CB out front, and it's multiplied by all of this stuff in here. Okay, and then same thing when you come down to calculate this capacity, right? It's going to be FCR times SX. Well, FCR has got a big CB out front, and so there'd be a big CB right in front of that equation. Imagine pulling the CB out of there, okay? And so what we do is we take that CB and we put it on the other side of the equation, okay? And so we go like this. We say, we're going to come up with this new, we're going to adjust our demand. We're going to say mu adjusted is equal to mu divided by CB. And then that will be less than or equal to phi times the stuff. Okay? And this stuff is in the curves. This is what's plotted in the curves. In 310, right? No, those are 310, 310. Yep, and 310. Okay, and so what the curve plots is, right, CB equal to 1, right? So it would just be this stuff right here, right? I've pulled the CB, I've moved it over to my demand side of things. And so what you do is you enter the curves. AISC is no dummy. Enter capacity curves with MU adjusted. Okay, so we change the demand so that we can use design aid. Okay. Careful though. B does not apply to plastic moment capacity. VMP. You got to be a little bit careful of that, and we'll cover that. There's a way to avoid that. Oh, actually, we can do that right now. Let me keep going with this, right? So what we're doing is we're adjusting our capacity, and so we enter those curves with a smaller, right? CB is going to be greater than 1, so you're going to enter the curves with a smaller MU. When you go to plot it, it's going to be 1.67. It's going to be your actual demand divided by 1.67, so that you can use those curves to help you with the design. But you got to be careful, because if you look at those equations for our MP equations, our VMP equation, there is no CB out front. So you got to be a little bit careful. Okay, you got to make sure that you don't violate this VMP thing. Okay, and I think the easiest way over the years that I've taught, sometimes you guys have a little issue wrapping your head around what's happening there, but if I give you like a procedure, I think you can handle it. Not that you all, I mean, there's a bunch of you that get it, and I'm not trying to insult you in any way, but just out of years of experience, I myself have a little bit of issue, and I'm a doctor, okay? But again, this only applies to lateral torsional buckling. It doesn't apply to VMP. So you have to make sure that the beam you come up with, your demand is not greater than the plastic moment capacity. Okay, because you could do that. Okay, but we'll see that in an example later. So we're going to design for MU adjusted. I think I call it ADJ. Okay, and then after we do that, that's all right. I'm going to make a procedure here. Okay, we're going to start out. We're designed for MU adjusted. Then we're going to check that MU is not greater than VMP. Okay, this MU is the not adjusted MU. This is just the MU of the thing. Okay, if it is, if MU is greater than VMP, plastic moment controls, and design with Z tables. Okay, and we'll see that play out in an example. But at the very least, if you understand this, right, we got these CBs floating around to account for these different loading conditions, or the different end conditions, and the severity of how much of the compression flange is in compression at what severity, right? This versus this, for instance, right? This is going to be worse than this, right? And so you got the CB floating around for that. To go for these design, they've come up with these beautiful these beautiful capacity curves, and we're going to plot it and read up and to the right. But all of these capacity curves are for one CB value. And you saw those CB values range from 1 to 1.67, I think is the biggest one that I saw there. So you can't come up with capacity curves for all of the different CB values. It wouldn't be economical, right? Think how big that steel manual is now. I think it would be super huge, because you'd have all of these different CB values floating around. And so what we do is we kind of decrease our demand by dividing by the CB value, and then we enter these curves with this decreased demand. Okay, but then you got to be careful, because that CB accounts for these capacities. It affects these capacities, I should say, but it does not affect these capacities, right? And so there is a tendency, if you designed this thing for a reduced MU, right, that it might look like it's going to work, but really that reduced MU, or so it's like shows up like right here, so versus that blue, it shows up right here, but then that's the reduced MU. If you actually look at your real MU, By not dividing by CB, which the plastic moment capacity is not, it would actually be up here someplace. And so that would be in violation. So that's what this last little step does, right? Is we design for MU adjusted, but just afterwards, you just got to make sure that your unadjusted MU is not greater than phi MP. Okay, and if it is, then that means the plastic moment controls, and it's not lateral torsional buckling that controls, and then you could just design with the Z tables. Okay, we'll do that in an example next time, right? And that's going to be this guy right here. We're going to design that sucker right here. And so I'll try to post that example on Tuesday this week, so you have time to finish the your homework there. All right, and then after this, that's it for beams, by the way. The last thing we have is columns and buckling. And I think we can finish that up in maybe 2 more lectures. We're going to do this example and then maybe 2 more lectures, and then we'll call it good. Hope people are staying safe and healthy, and hope everybody's doing well.